but getting in situ atomic level structural information is more challenging. Although recovery, you could get information upon recovery. So with new capabilities for in situ atomic level structural information with new X-ray sources, that has really opened up new frontiers in dynamic compression, allowing one to address scientific questions such as just the behavior of matter under extreme conditions, testing theoretical predictions, looking for new states of matter, understanding exoplanet interiors and dynamics, and these are also relevant for planetary formation processes. And the figure on the left is just a very schematic illustration showing sort of the range of pressures and temperatures that may be of interest in understanding exoplanets. So we're talking about a few terapascals and many thousands of Kelvin. So that's a challenge to be able to access those sorts of conditions and make measurements under those conditions. So the drivers, this just highlights this a little bit more, the various drivers that are available. So traditionally in the upper left, we see sort of a gas gun plate impact type of experiment, which has been used for 50, 60 years and extends to pressures of typically a few hundred gigapascals. Then in the upper right and lower left are two very schematic illustrations of laser-based dynamic compression experiments where a high-powered laser is used to ablate a sample surface, and that drives by reaction, that drives a compression wave into the sample. And this can be performed using, the types of experiments that can be performed include decaying shock experiments, and that's what's illustrated in B, or in C, steady shock or ramp loading, depending on the nature of the experiment, the nature of the laser drive. And then D is a schematic illustration of a pulse power system, which provides another means to drive compression waves into a sample at a somewhat longer time scale than these laser drives. So I'll be focusing on ramp compression. And now the figure on the left shows the typical shock wave, which is an extremely rapid rise in the ideal case as a result of impulsive loading of a surface. And contrast that with ramp compression, which is shown on the right-hand side of that figure, in which the material is compressed over a longer time scale, say order tens to hundreds of nanoseconds. For laser-based dynamic compression, it's order tens of nanoseconds. And a way to visualize this is, as indicated by the dashed curve, is it's akin to breaking the compression wave into a series of small shocks. And each shock achieves a much smaller volume change or compression. And so the shock heating and entropy creation is reduced. So a greater fraction of the energy goes into PDV compression work. Now, in the limit of an infinite number of shocks, the amplitude of each shock approaches zero, and this approaches a shockless isentropic compression curve. We can't achieve that in practice. There will be some dissipative processes such as plastic work heating, which results in some heating and some entropy increase. But there are some real advantages to this technique in comparison to standard shock loading. First of all, you can compress materials to very high pressure while avoiding melting. So usually when you're shocking something, you get to a couple hundred GPa or so, many materials will have melted. So you can go to higher pressure without melting. Also, you can just get to higher pressure in general. Again, with shock experiments, you tend to, as you go to higher and higher loading, the energy tends to get partitioned more into heating than compression. So you end up just mostly heating the material. So there's sort of a limit into how much compression you can produce. And you don't have that limit in ramp compression. So you can go to very high, much higher levels of compression than you typically can in a shock experiment. But everything has its advantages and disadvantages, right? Ram compression is a bit unstable. You want to avoid forming a shock. That's sometimes hard to do. And it's a little bit more challenging to determine the pressure conditions, and temperature is often fairly uncertain. So the figure on the right here is an example of sort of a schematic pressure temperature illustration for a particular material, iron, that shows that actually in practice what happens is that it's not just purely ramp compression, but we usually initially end up with a shock in the sample. So that shock could be 50 to 100 GPa or so, or maybe even more. And then you ramp compress to higher pressure after that shock. So you get a component of heating initially due to temperature, due to the shock compression, and then you isentropically compress to higher pressure. So that enables you to sort of access sort of a wide range of PT states in between the principal isentrope and the Hugonium. And so that's a real advantage of the technique. So the experiments that I'm going to talk about here were mostly performed at the Omega Laser Facility at the Laboratory for Laser Energetics at the University of Rochester. So Omega consists of two laser systems, Omega 60 and Omega EP, and both of them are useful for ram compression experiments. Omega 60 is a laser with 60 individual beams, each of which can be timed and positioned differently. And Omega EP is four separate lasers, again, each with independent controls. So these operate at 351 nanometers, and they can deliver up to kilojoules of energy up to 10 nanoseconds. The pulse lengths can be up to 10 nanoseconds on targets that are order millimeter in size. And the repetition rate is roughly, very roughly about 1 shot per hour. So in a day, you can maybe get 12 shots or something. So it's a pretty good shot rate. On the right at the top is a figure showing a laser drive from Omega. So this is the power in terawatts as a function of time for a 10 nanosecond pulse, showing a ramp-shaped pulse. So you can design the pulse or use one of the available pulses to control the type of loading that you're going to apply to the sample. So this is an example of a ramp load that we would apply. And there's an empirical scaling law shown below, which relates the pressure that should be in GPa to the irradiance in terawatts per square centimeter, divided by the wavelength here. And the bottom line is for irradiances of 1 to 30 terawatts per square centimeter, we can access pressures of 100 to 1 terapascal. And that's sort of that's a range that's readily achievable with this system. So, compared to tools like the diamond anvil cell or say plate impact shock compression, which tend to get really difficult above 200 GPa or so, this gives us the ability to extend that by a factor of 5 or even more, even 10, and get to higher pressures. But what can we do with those pressures? Actually, let me talk about this figure on the upper left here. Again, a very schematic illustration of the experimental geometry. The green band here is the sample, and so it's sandwiched between an ablator on the left side and a window on the right side. These are often both made of diamond. Sometimes the window is lithium fluoride, but basically the front diamond acts as the ablator. We drive off a plasma at high velocity, heating it intensively, and drive a compression wave into the sample, which reverberates between the two windows and rapidly brings the sample up to an equilibrium state. And then this is attached to a metal foil with a hole in it. That gives us access for an interferometer that we can use to measure pressure and enables us to collimate an X-ray beam that we generate in order to carry out diffraction experiments. A little bit more on the schematic of that. So the way it's laid out is shown on the right here. The target package is this little gray rectangle, this little gray square here. And some more details of the target package are shown here, showing some of the dimensions. The sample thicknesses are typically 10 or 15 microns thick, and the diamonds are and the window are maybe 40 to 100 microns. So that gets mounted on the front of a box, and we drive it with laser beams from omega 60 or omega EP. And then other beams are used to generate an X-ray source, a laser plasma X-ray source by very high irradiance of a metal foil, which produces an X-ray spectrum, which is dominated by helium alpha line. So this is an example. This is from a paper by Federica Copari, and this is an example of a germanium X-ray source at about 10 keV, showing that we can get a line with about 100. Typically, you get about 100 or so EV line width. There are some satellite lines, so it's not completely monochromatic, but there are some satellite lines that need to get suppressed with some filtering. And we can use other materials as well, iron, copper. So you can cover energies from roughly, I think, about 6.5 to 10 here keV in terms of the energies that you can access with this so-called backlight or plasma X-ray source. And so that X-ray source generates X-rays, which then pass through the sample, diffract from the sample. They get collimated by this pinhole behind the sample. And then they impinge on image plates, which line the walls of this box. So we're going back to the old-fashioned image plates for detecting these X-rays. And there's a hole in the back of the box that allows an interferometer to access the sample. So I want to mention, what the limitations are that we have to worry about when we're doing these types of experiments. The X-ray source is very bright, but it's also uncollimated. So and this is 25 millimeters or so away from the sample. So the amount of X-rays that you generate that actually get through the pinhole you lose a lot of them in the process. There's also a pretty strong X-ray background, particularly at higher pressures, that arises due to the plasma that you generate during the laser drive. And as a result of that, typically you can observe a few strong diffraction lines, typically maybe 1 to 3, sometimes more. Depends on the pressure range and the particular characteristics of the material. So so I want to make it clear that there are, that these are really challenging conditions, but we can actually do really quite well with these, as you will see. So here's one example. So this is some work that was done by Cyrus Hahn, a graduate student at Princeton, and just to show really quickly, gold, would be a good candidate. So materials that are good candidates for this are things that have relatively simple diffraction patterns and high atomic number. Gold is a good candidate for that. And in Cyrus's work, he's shown that gold will transform under ramp loading from a FCC indicated by these purple or magenta circles to the bluish color here, which is the BCC phase. And that's at around 234 GPa, and then the BCC phase remains stable to 690 GPa. So plotting his data, sort of a lower bound temperature on a phase diagram as shown here. So we get this transition that's at lower pressure than predicted by some theoretical calculations, but it is consistent with recent shockwave data from Livermore and from Washington State University that also see this transition under shock loading at comparable pressures. So a number of different metals like this have been done, and a number of different phase transitions have been observed, and so we've learned a lot about these simple metals. But what about planetary materials? So that's what I really want to focus on here. And of course, there's been a discovery of a huge number of extrasolar planets from the Kepler mission and other spacecraft missions in recent years. And the figure on the left shows a quantity of these from the Kepler mission, showing the radius in terms of Earth radii as a function of orbital period. And you can see that it's this region in between the Earth and Neptune that has the real high abundance of planets. Now, in our solar system, we have planets that bracket this, but we don't have anything within in this range. So this raises the question of what type of planets are these, and how do they work? And of course, there's been many ideas have been proposed. There may be Earth-like planets that are up to, say, like 10 Earth masses in size, super Earths, or there could be super Ganymede type planets that have rich in water, or Mercury type planets that are very iron rich. And another type of planet that I'll be talking about that has been proposed are carbon rich planets that have a very different mineralogy compared to terrestrial planets. So why are we interested in the interior structure of these things? Well, I think the way it works is, we need to know what the basic phases are that can exist in the deep interiors of these planets. And we've been studying materials like oxides, silicates, carbides, germanates. Germanates basically is an analog. There's a wide range of materials that one would be interested in, because the discovery of all these exoplanets has opened the door to a much wider range of possible interior compositions than we have with the terrestrial planets in our own solar system. So not only is the compositional space much larger, but so is the pressure and temperature space. So the figure on the left here shows a comparison, very cartoon comparison of the Earth with a 10 Earth mass terrestrial planet. And the pressure at the core mantle boundary and the pressure in the center of the Earth for this super Earth are roughly an order of magnitude larger than they are for the Earth. So we have pressures into a few terapascals where we have to explore the behavior of material. And so, the crystal structure or the atomic level structure is the most fundamental piece of information, and other properties that you're interested in follow from that. For instance, phase transitions can be very important in the interior dynamics of a planet. These calculations, these simulations on the right are from Dave Ewan and Vandenberg, who are looking at a variety of different sized planets with phase transitions in the interior that generate changes in the dynamics, as you can see. So the dynamics of the interior depend on the structural variation of the phases in the interior. But beyond that, of course, you also need to know all the physical properties that follow from the chemistry and the structure: thermal expansivity, thermal conductivity, metallization, or electrical conductivity, all these things. So, but the structure itself and the equation of state are sort of the most fundamental pieces of information. And I want to also emphasize a little bit how the interior structure is one component of understanding extrasolar planets as a whole. And so I kind of like this figure that kind of shows all the different sort of approaches that you have to take to understand these exoplanets. And this is something that's going to be a long-running project as new spacecraft missions get developed and analytical techniques improve and so on. But in the upper left here, the properties of the host stars need to be well understood: the composition, the radius, and many other properties. Then there are the orbital characteristics of the planetary system as a whole. And then there are the individual planetary properties, whether it's the orbital dynamics, what's the semi-major axis, the eccentricity, and those sorts of things. What's the surface like? What is the surface temperature? And what's the albedo of the surface? What is the atmosphere like? What is the composition? What are the cloud structure? And all those sorts of properties. And an important component of this as well is what's going on in the interior. That gives us constraints on the density, the magnetic field. The interior influences the atmosphere. It influences the surface tectonics, the existence of plate tectonics, volcanism, and plays a major role in the thermal evolution of a planet. So there's all these components that have to go into understanding extrasolar planets. The interior is an important aspect of that. All right, so the first material I want to talk about here, and actually the main one I'm going to emphasize is silicon carbide. And this is the work of Dong-Hoon Kim, who I mentioned before. So silicon carbide, forgetting about planetary implications, it's an important material. It's a ceramic. It's one of the major non-oxide ceramics. It has very strong covalent bonding. It's got a lot of desirable properties that make it extremely widely used. It's high melting temperature, hard, chemically inert, lightweight, high thermal conductivity, and on and on and on. So it's something that can be used as an armor for protection. It's been considered as an ICF, inertial confinement fusion or fusion reactor components. Its electrical properties make it useful as a semiconductor. It's been proposed and calibrated as a candidate pressure standard. And it's kind of an archetype for one of the fundamental phase transitions in simple binary solids, the B3 zinc blend transition to the B1 rock salt phase transition, shown here. So it's an interesting and important material as an engineering material in its own right. It's also been proposed as an important constituent of a possible class of planets known as carbon planets. So carbon planets are planetary systems with a very high carbon to oxygen ratio. So the carbon to oxygen ratio has to be greater than 0.8 or so. And in this case, if you look at the condensation sequence that would occur from such a nebular gas of this type of composition, you end up condensing carbides, not silicates. The oxygen gets locked up in things like carbon monoxide or methane, and you end up with various types of carbides. So in the simplest case, a carbon planet can actually be very simple. It can just be a mixture of silicon carbide, possibly excess carbon in the form of diamond or graphite, and then an iron alloy core. Now, the carbon-oxygen ratio of the sun is 0.55, so it's considerably lower than this high value. Now, very recently, the paper was published, a survey of 47,000 stars, and they determined the carbon-oxygen ratio of some subset of these. They couldn't determine for all of them. So not a lot of them have this high carbon-to-oxygen ratio, actually about 1%, and those are indicated by these open symbols here. Nevertheless, there are thought to be a humongous number of planets in our galaxy, so 1% is still a lot of planets. It's also been proposed that planets don't exactly reflect the composition of their host star, and you can have processes in the surrounding disk that can concentrate, some chemical components. So it's been suggested that you may get carbon-rich planets even for much lower C/A ratios, which would expand the number of candidate stars quite a lot. But even if they're rare, even if they're extremely rare, even if this 1% is a bit of an overestimate, I would still argue that they're worth exploring because they would be a highly exotic planetary style, completely unlike anything we have in our solar system, because silicon carbide has this very high melting temperature. It tends to be strong, low thermal expansion, high thermal conductivity. All these properties are quite different from silicates. So this would be an interesting type of planetary style to explore. All right, so this is the thesis work of Dong-Hoon, as I mentioned, and here's just an example of some of his results. So the figure on the left, again, is a schematic illustration, maybe a little bit simpler, of the diffraction geometry. You have an X-ray source, drive beams on your sample, the X-rays pass through the sample, get collimated by a pinhole, and diffracted X-rays are recorded on image plates. On the upper right is just a raw image plate, just so you can see what that kind of looks like. You can see a couple of rings here from the sample. One is here, and the other is here. You also see some lines from tungsten. That is the pinhole substrate. And so that's just used to calibrate the geometry here. And in this particular experiment, the sample was backed by a lithium fluoride window, and the lithium fluoride tends to break up during it's a single crystal, it tends to break up, so you get a bit of a smeared out diffraction from the lithium fluoride here. So if you translate this to coordinates of d-spacing versus phi, where phi is the azimuthal angle around the X-ray beam, you can see the two clear lines from silicon carbide here, the 111 and the 002 from the B1 phase of silicon carbide, together with the lithium fluoride and tungsten lines. And this one-dimensional line out here is integrated from the region in between the blue lines here. So that's a typical experiment. So the experiments ran from 80 GPa all the way up to 1500 GPa, and 1 to 4 diffraction lines are observed from the sample, mostly 1 or 2. At 80 GPa, the B3 zinc blende structure was observed. We weren't really focusing on low pressure, so the next pressure was 140 GPa, and that's we observed the B1 rock salt structure. It's known from static and shockwave experiments. There's a very large density change associated with this transition by like 20%. But then we observed the B1 structure all the way up to 1500 GPa. So these are just a few sample diffraction images in d-spacing azimuth space. So here you can see at 140 GPa, you get the nice diffraction line from the 200 peak, and you can follow it. Here it is at 300 GPa, 500 and something, 900, starting to get weak around 1,000 and barely visible here at 1,500. But you also see another line coming in here, the 111 line that we sometimes see here. The yellow dashed or golden dashed lines, orange, I guess, are pinhole materials. And the circled, the green circles represent basically diffraction spots from single crystal like diamond or lithium fluoride. The main limitation really is that the plasma background grows pretty rapidly at high pressure, and it moves to higher energy, so it starts to overlap the energy of our X-ray source. So the signal to noise ratio becomes more and more challenging as one gets to higher pressure. But we can do these line outs, and you can trace these peaks up to the highest pressure. So so the other thing we have to do is stress determination. So for that, a line imaging velocity interferometer system known as VISAR is used. And that will either measure the interface velocity between the sample and a lithium fluoride window if we're using lithium fluoride. If we're using diamond, instead we measure the free surface velocity of that diamond. And so as the surface starts to move, the reflected laser light is Doppler shifted. That gets analyzed in an interferometer where the light is interfered with light that left the sample slightly earlier due to a little bit of a delay lag, and that produces interference fringes which are sensitive to velocity. And again, it's a line image here. So representative data is shown on the right here. This is for a relatively low pressure experiment with the lithium fluoride window. Again, we have this ramp drive shown in blue, and the X-ray generating pulse is shown in red. The VISAR fringes are shown here, and the resultant velocity. There's actually two different VISARs, but they basically record the same thing. So those are red and blue. And what we do is, in this particular case, is we use an equation of state for each target layer. And we take an initial estimate of stress from our scaling law. And then we do a hydrodynamic simulation of the experiment to match the observed velocity history with the simulation. And that's what this light blue line is. It's the simulated velocity. And from that, then we can make a map of stress as a function of position and time in the sample, which is shown here in these color contours. And so the silicon layer is here, and the time of the X-ray source is shown by these vertical dashed lines. So the X-ray source was, I guess, 2 nanoseconds or something here. And then we can take a histogram of all the stresses within this time and spatial region and average those to get the stress in the sample, which in this case was 371 GPa with some uncertainty that I haven't listed here. In the case of a diamond window, it's done in a somewhat different way, but nevertheless, it's in general, it's a comparable approach. So that's how we get the stresses in these experiments. And so from the measured d-spacing and the stresses, we can map out the dependence of d-spacing on stress as shown here. So again, we have one data point in the B3 structure, and then a pretty reasonably dense accumulation of data in the B1 structure. The solid lines, the black and blue, are extrapolated, predicted d-spacings from the extrapolation of the equation of state from diamond anvil cell data. There were a couple of different studies, and our results are consistent with that out to the highest pressure. We also have some diamond peaks that are observed. Those were those spots. So basically that's the diamond 111 line that we see here in the 220. Okay, so we have this, we can get d-spacing over a very wide range. Then we can calculate density as a function of stress out to 1500 GPa, 1.5 TPa. So the red line is a Birch-Murnaghan equation of state fit to our data. We get a bulk modulus of about 280 gigapascals and a pressure derivative of 3.8. Our results are actually in very good agreement with theoretical calculations, 0 Kelvin theoretical calculations of Wilson and Millitzer from a few years back. The agreement is so good that you actually can't see the Wilson and Millitzer line here. It's completely underneath our red line. It's very good agreement between theory and experiment. That's actually, I think that's a really useful part of these experiments, is the ability to compare and test with theoretical calculations. There's actually been a huge number of theoretical calculations of silicon carbide over the years. They don't all agree with our work. Actually, there's quite a wide range. This yellow band shows all the cold models that have been reported in the literature over the years. So there's quite a wide band. Ours are consistent with the highest densities here, consistent with these recent calculations from Burkhardt-Millitzer's group. We can also test the two different diamond cell experiments. So our results appear to be in better agreement with the diamond cell data of Kitakoro compared to another study. So that's another useful aspect of this data. And just to mention that, at the peak stress, we're over 10 grams per cubic centimeter. So that's more than threefold compression relative to ambient conditions. And, the earlier static and diamond cell data is shown down here. We've increased the covered pressure range by a factor of 7. So those are the nice features of this technique. You can cover a wide range of compression and pressure. Okay, well, there's always a question about temperature. So what temperatures are achieved in these experiments? And there's honestly considerable uncertainty about that. So again, here would be a principal isentrope for silicon carbide. We don't quite have that in several senses. First of all, we have an initial shock in the sample, and it's maybe about 50 GPa or so in the sample. So you heat the sample to like 500 centigrade or so, and then we could calculate, assuming we just follow an isentrope from that point on, and we would get these temperatures here, which would be a bit less than 2000 Kelvin at the highest pressure. There's additional components of heating due to plastic work as a result of material strength. That's a bit more uncertain. We don't really know what the strength is of silicon carbide under these conditions. There's low pressure measurements of strength. So we just sort of assumed that those values could be applied to higher pressures, higher stresses. And so we got these sort of estimates of the temperature. So that sort of shows the sort of expected range of temperatures. it's really quite different from the Hugonio, which rises very steeply here in the melting curve. And so we're sampling, again, a different region of temperature stress state, which provides, sort of a unique set of data. Okay, so this figure shows a number of planets that have been observed. So this is a radius mass diagram showing a large number of observed planets as the open circles there. And we've put a number of things on this plot, one of which is hypothetical single component planets. So that's useful for sort of evaluating the possible compositional space of all these planets. So you could have a pure H2O planet, or a pure diamond planet, or a pure silicon carbide planet, pure MgSiO3 planet, or pure iron planet. And you can see that, of course, there's going to be a lot of degeneracy here. There are a lot of, they're not really unique solutions. An Earth-like rocky planet, so with about a core that's about 30% by mass, shown by this this green band. And carbon planets, based on our experimental data, are less dense than that. So we have a bigger radius for a given mass. The pink band would just be a very simple pure silicon carbide mantle with an iron alloy core, and the gray band would include an equal mixture of silicon carbide and carbon in the interior. So carbon planets are a bit less dense than rocky planets, and this shows sort of the range of type of behavior that we could have. And I think it's important to emphasize that the nice feature about this is that it's experimentally constrained, which is in most cases not the case. I mean, most of these exoplanet interior models are based on an extrapolation or theoretical calculations that haven't been confirmed yet by experiment. So I think we want to push towards the situation where we can directly measure these various planetary constituents. So you can go further and look at what the interior structure model would look like, and start to think about what this type of planet would be like. There would be a major structural discontinuity near the surface. This is for an 8 Earth mass carbide planet. The B3 to B1 phase transition would be a major feature because it's got such a large density change, a negative Clapeyron slope. It's the type of thing that you would really expect would probably result in layered convection. The core mantle boundary pressure is about 1 terapascal, and the central pressure is about 3.4 terapascals for a 30% core by mass. These are similar to what you get in a silicate oxide rocky planet. And you can do different combinations of things to get constraints on the central pressures for different models, and constraints on the density. So that's the type of basic structural model that you can solve for this. So we're starting to get data on a number of say exoplanet mantle materials, direct experimental data under ramp compression. So in addition to Dong-Hoon's work on silicon carbide, in our work with Federica Copari, she's produced data on MgO and also very recently on FeO. Amy Lizicki recently published equation of state X-ray of diamond out to 2 terapascals. So those data are shown here. Here at the bottom in compression stress state. You can see that getting up to compressions of a factor of 3, and as I said, stresses can be as high as 2,000 GPa. So that's the start of collecting this sort of direct experimental data on these planetary materials. But actually, there's a long way to go, because the composition of rocky exoplanets are likely very diverse, as I indicated before. The figure on the left is also from this paper, this survey of 47,000 stars that I mentioned earlier, showing in this ternary diagram, MgFeSi, showing a wide range of composition. So you have iron-enriched planets. These red circles here Earth and the sun. So you have iron-enriched, magnesium-enriched, silicon-enriched planets just within this ternary composition space. And the figure on the right is another very recent paper in which they compared the iron content of the host star to the iron content of the planet that's derived just from the mass and radius, the density. And they found a positive correlation. So the planets really do reflect their host star. More iron-rich stars tend to produce more iron-rich planets. But note that the planets are actually quite enriched in general. They're quite enriched in iron relative to the host star. So while planets reflect the host star, they can also be enriched in these components. So this is just a starting point. You can have enrichment in these chemical elements beyond just what is in the host star. So I want to highlight Federica Copari's work that was published earlier this year in Nature Geoscience. And this is kind of a summary of it. This shows the earlier data for MgO here, and her new data on iron oxide is shown here. Interesting feature. So again, there's a major phase transition in this system from the B1 rock salt is now the low pressure phase, transitioning to the B2 cesium chloride phase, the high pressure phase here. And it's a big difference in the B1, B2 transition pressure. So in MgO, it's around 600 GPa in these dynamic experiments. In FeO, it's already in the B2 phase at around 300 GPa. So this system, which at lower pressures has complete solid solution, has very different transition pressures. I would also note that the important role of iron, because I think if you look in the last 5 years or so between theoretical calculations and experimental studies, there's probably 10 papers on MgO, but very, very little work on iron oxide. I think Federica's work is one of the few, and almost no work on intermediate compositions. In fact, there has really been no work on these intermediate compositions for like 40 years. This is like 40-year-old data. So Ian Ocampo, who's a grad student at Princeton, is working on intermediate MgFeO compositions for his thesis. I'm not going to show any of that data today, but just to emphasize the importance of these intermediate compositions. Now, based on what we know about the Earth, the deepest part of the Earth's mantle is a mixture of ferropericlase, MgFeO, and this post-perovskite silicate phase. It's pretty hard to measure partitioning of iron between these two phases. The results are, it's very high pressure, and the results aren't super reproducible, it seems. It's complicated, though. There's some complicated factors. But it does seem that iron partitions very strongly into ferropericlase. So iron-rich ferropericlase is probably very important, although we do need to measure these partition coefficients at much higher pressures and higher iron contents than has been done so far. Anyway, based on the data that Federica obtained, she produced an ideal mixing model. So this is kind of a simple end-member type of model in which there's a very broad B1, B2 phase loop extending over 100 GPa or so in this system for a composition that has, say, 40 mole percent iron. And the interesting thing, there's a couple of interesting things about this. Let me skip to the next slide and I'll come back to this. The first is a theoretical calculation that was done by Sebastian Ritterbeck out of the Lille group. And he studied atomic diffusivity and the migration of vacancies in MgO, just pure MgO, across the B1, B2 phase transition. And so, for instance, the migration enthalpy of a vacancy for oxygen drastically declines across the B1, B2 phase transition, as does magnesium. So his conclusion is basically that this transition produces a big increase in atomic diffusivity, enhancing diffusion creep, and could lead to as much as 4 orders of magnitude reduction in viscosity. So this phase transition can be really significant if it's occurring inside an exoplanet. So in Federica's ideal mixing model here, you'd have for say a 5 Earth mass exoplanet, you would have a region of bridgemanite and ferropericlase, then post-perovskite and ferropericlase. But then you'd get this mixed B1, B2 region, and then finally a B2 region where the viscosity could actually go down, which is the complete opposite of what one's intuition is, that the viscosity is going to increase with increasing depth in these planets. So you may have a very unusual structure in these planets, as a low viscosity region could affect heat flow, it could affect the behavior of the magnetic field, could have a lot of implications that are discussed in Federica's paper. The other thing I want to highlight, though, is that you could have a lot of other things going on. This is just a preprint, and I don't want to go into it too much, but some theoretical work on ferropericlase suggests that you may have, you can have a structural distortion, you can have a spin transition from low spin to intermediate spin, you can have metallization. So there's a lot of things that could also be going on here. So it's a rich system to try and understand, and we're at an early stage of that. So for the last thing I want to briefly talk about is, what about silicates? Here I'll focus your attention on some theoretical calculations by Umamoto and Renato Wenskevich, which are really interesting. They looked at the MgO SiO2 system for different compositions. Let's focus on the middle panel here, which is MgO rich, Mg-SiO ratio greater than 1. And so the phases that are familiar from Earth's interior, like bridgemanite, perovskite, post-perovskite, those phases remain stable to about 400 or 500 GPa. And then they find that there are these new structures, okay? And these new structures have stoichiometries like Mg2SiO4 or Mg-Si2O5. And the interesting thing about these is they're highly coordinated. The post-perovskite phase has a coordination number of 6, but these phases can have coordination number of 7, even 8. Okay, and changes in coordination are important factors in planetary interiors because there are a lot of changes in properties that go along with them. So it's important to try and test these sort of theoretical predictions. So how can we do that? Well, we're doing a multi-pronged effort, but I'm only going to really show one thing, which is going back to the diamond anvil cell. So let's go back to the diamond anvil cell a bit. 500 GPa is a very tall order for the diamond anvil cell, particularly you need several thousand Kelvin. So one approach is to use germinates. So this is really long-standing. I actually really like the fact that we're going back to something that was done back in 1963. Ringwood, because he didn't have the technical capability to go to very high pressures, he used germanates as analogs for silicates, because germanium is right below silicon in the periodic table and has a larger ionic radius. It's a good analog. And in the 60 years since this time, there's still many applications for these germanates. Yanbin Wang, for instance, is using them to understand deep earthquakes in the Earth, for instance, and others as well. Umamoto and Wenskevich have predicted that similar transformations should occur in germanates, but at lower pressures, more like 180 GPa, 200 GPa. So that's still a challenge for diamond anvil cell experiments, but it's more feasible. And so I'm going to just very briefly highlight a little bit of work of Raj Dutta, who it takes a lot of skill to do these experiments, and he has studied this magnesium germanate composition up to I think 260 GPa or so, and temperatures above 4,000 Kelvin. And he discovered above 180 GPa a new phase. It's a thorium phosphide phase. It's a cubic structure, and it's a body-centered cubic lattice. And this shows an example of one of his diffraction patterns, some 5 or so nice clear peaks of the new phase. I'll leave it to Raj to discuss details of this in his presentations later, and just mention a few points about this particular phase. It's interesting for a number of reasons. First of all, it's the first occurrence, as far as we are aware, of this thorium phosphide phase in any kind of oxide or germanate or anything like that. It's common in rare earth sesquioxides, but it's never been observed before in this type of group. It's also cation disordered. So magnesium and germanium actually share the same site, despite their very different properties, different charge and size. And finally, germanium adopts eightfold coordination. So as far as we are aware, it's the first synthesis of an 8-coordinated germanate. So this by the way, I should say that this phase is not quite the phase Umamoto predicted, but it's a related phase. It's a disordered version of the phase that Umamoto predicted. So this is an important candidate. And if I go, let's see, if I go back here, I point out that basically, if this similar phase transition is happening in the silicate, it sort of corresponds to sort of a 4 or 5 Earth mass planet. And this is actually similar to the MGO result, where the B1, B2 phase transition is also something that occurs basically around a 4 to 5 Earth mass planet. In other words, if you're less than sort of, say, 4 Earth masses, you basically have the familiar structures in your mantle. You have postperovskite, you have ferropericlates. But if you get above 4 to 5 Earth masses, then you can get these new highly coordinated phases, the B2 phase, and this thorium phosphide phase. So it seems like there's a boundary where you may get very different behavior in planets between about 4 and 5 Earth masses. So quickly, let me finish up quickly, just 2 more slides. We're also pursuing these silicates under ramp compression. So we have a project ongoing at the National Ignition Facility, which has similar X-ray diffraction capability as the Omega laser, but has certainly NIF has some advantages. Significantly higher energy and longer pulse lengths give it a real advantage, I think, for diffraction experiments. But the limitation is you only get sort of 1 shot a day. So the shot rate is rather low, so it's not so easy to cover a wide range of pressure space. But this is something that Cyrus Hahn is working on with Martin Gorman and Ray Smith at Lawrence Livermore National Lab. We actually have a shot next week, so hopefully we'll have some new results on this, but I don't really, we're still at an early stage in this project, so I won't say anything more about it right now. So that's really it. I'm out of time here. I just tried to show that dynamic ramp compression gives us a novel capability to study structures up to terapascal pressures. I've tried to be, I think, fairly honest about the strengths and weaknesses of the technique. I think the important things about it are we can get direct experimental data at these conditions. In combination with theory and modeling, we can make advances in understanding extrasolar planets. And you know, our results today are so far pretty limited. There's many more things to be studied, but one thing that's emerging is that you know, for these oxide silicate planets, as I indicated, sort of 4 to 5 Earth masses seems to be a critical size, as there's going to be major differences in the mineralogy above and below that. And we've also been able to sort of delineate how a highly reduced silicon carbide planet might behave at extreme, might look structurally at extreme conditions. So again, thanks very much. I greatly appreciate having the opportunity to present this to everybody.
Thank you very much, Tom, for your overview of a really interesting current topic. Sure, there's many questions out there. Please either unmute yourself, or you can put your question in the chat box.
Tom, sorry, Nanad here from HPCat. So a question, actually I have a couple of questions, I'll bundle it into one. When you talk about ramp compression, and especially like your slide on silicon carbide, you have the laser power, dry power plotted. So I guess my question is this: when you have a large volume collapse in like silicon carbide, where you have 20% volume collapse, how difficult is it to keep the sample from shocking up as you go across these large volume collapse transitions? Can you actually control it? And also along those lines, does kinetics of phase transition play a role in how you actually do pre-shot, you know, calculations and modeling to keep it quasi-isotropic?
Yeah, those are both great questions. So phase transitions can be a can be a problem because materials tend to shock up. In this case, I think because the transition is fairly low pressure, we didn't see any evidence of shocking up in this case. So I think, but you're right, it is a very large volume change. So, but there was no shock wave in the visor. And then kinetics are obviously important. So it's clear that in certain cases, well, for instance, in the silicon carbide, the static work suggests, I don't know the exact number, Dong-Hoon or someone would know, but maybe that phase transition occurs at 50 or 60 GPa, and we're still seeing the low pressure phase at 80 GPa. That's also true for shock waves, where you still see the low pressure phase up to a megabar. So that's the case. In other materials, we've often seen. We have other examples of where we've seen a particular phase that appears to remain stable to higher pressures than suggested from theoretical calculations. So that's definitely an issue. It's a little bit, in some cases, it's a little hard to come to a definite conclusion right now as to how significant that is. I think in the case of MGO, there's evidence for a little bit of kinetics, but it's not too much. But usually, I think we have to overdrive these transitions a bit before they occur. And of course, some transitions probably will never occur.
Thank you.
Okay, Felipe Gonzalez from UC Berkeley.
Hi, Thomas.
Go ahead, please.
Great talk. Thank you very much. I had a question regarding the RAM compression technique, and it is still not clear to me that the sample relaxes to a hydrostatic state, because the difference between the uniaxial pressure and the hydrostatic pressure could be very large. And my second question regarding to the planetary side, is there a reason not to consider other compositions in 10 masses, Earth masses, super Earths, like ISIS, or a considerably large gas envelope?
Yeah, so I was mainly focusing on more rocky, but definitely all the water-rich planets are also very important. And there are others who are working on that. I think like Dan Shim has done some really nice work on sort of mixtures of water and silicates. He had some recent work on that. So that's one example. There's other types of planets have been proposed as well, very refractory materials, which would be more like things like spinels and calcium aluminum phases. So there's a huge range of materials that we need to explore. In terms of your first question, let's see, you were asking about the non-hydrostatic stress. It's a good question. I think we can't really answer it right now. We don't know what the strength is. Silicon carbide is fairly strong at, it's a relatively high strength material, but all the data is the low pressure phase at relatively low pressures. So we don't really have any direct constraints on what's going on under these conditions. So I think an important area for the future is to get better constraints on strength. And you're certainly seeing that the folks at the Z machine are doing some nice measurements on strength. Of course, that's a different strain rate than these experiments. So there's also you have to worry about that comparison as well. So, but it's a good question. So that's what we call it, stress. We don't really know how different the hydrostatic pressure is. Yeah, that's all I can say about that.
Yes, we have a comment from Kanani Lee. The silicon carbide transition for the laser heated diamond anvil cell experiments show around 60 GPa, a negative Clapeyron slope for the transition. If under ramp compression, it is still observed at 80 GPa, that doesn't appear to be in conflict if the sample is not very hot. Okay, fair enough. Our estimates of the temperature are, somewhere between 500 and 1,000 Kelvin at those conditions. We weren't actually, actually doing the experiments at that low pressure is not
normal, and it was actually a little bit of an accident that we got data below about 80 GPa. So we don't normally do much below 100 GPa. So it was kind of fortuitous in that particular case. But there are, so if that one is more ambiguous, there are certainly other examples that we have where there's certainly evidence of needing to overdrive the transition. I think MGO, there's, if you compare June Wicks's data on, and Federica's data on the MGO transition, it's a little bit higher than theoretical calculations.
Yeah, I had a question, Tom, about given the pressure and temperature space on the super Earths, rocky super Earths, is it possible to predict whether differentiation, planetary differentiation, is going to be enhanced or suppressed? I mean, given the number of different coordination environments at these high pressures, compared to what we see in the Earth, for example.
Differentiation.
Yeah.
I mean, I think in the case of a carbide planet, because of the very high melting temperature, you probably have a very low viscosity. Sorry, very high viscosity, very high melting temperature, and therefore, melting is the primary agent of differentiation. So maybe much harder to achieve melting in the interior, and you may get much less differentiation. Of course, these planets are really big, and so the energetics of impacts are very, very large, and so you can that would go in the other direction, likely to enhance melting as the planets get larger. Is that what you had in mind?
Yeah, just given all the different effects, I'm just wondering if it's possible to predict or make a model for that, but I'm sure.
Yeah, I mean, I think there's room for future experiments on melting and volatilization, vaporization on impact. That's something, Sarah Stewart, for instance, has been doing on a large number of materials. And so that's an area for future work, and trying to understand what sort of species are produced and so on. So yeah, that's a rich area for future efforts.
Yeah, thank you. Are there any more questions out there for Tom? Well, if not, then please everyone join me in thanking Tom for an excellent talk, a wide-ranging overview, and best wishes on your experiments next week.
Yeah, thanks. Thanks, everyone. Appreciate having the opportunity to speak here.
All right. Thank you, Tom.
Yep.
Thank you.